times are not on Wednesday but on Saturday, on Tuesday, right, tomorrow. So this week there will be no PS. There will be, I will not hold the class on Wednesday, and the PS will not be held again. And I asked the TA to move us to Z06. If it is available, we will see. So the operating system, again, it abstracts the hardware for us. Talking directly to the hardware is bad in terms of abstraction because I cannot write portable code. Also, it is bad for the managing resources. This one says that operating system provides protection. Providing protection is somehow under this topic of managing the resources, because if you manage your resources right, then that means that you are providing protection too. What do I mean by providing protection? Two processes, two threads or two users should not interfere with each other. Each should have its own memory, it should have its own network, and I should not have any access to the memory of the other processes or the other users. Okay, so that's protection provided by the operating system. Again, it is under this managing resources. When you are managing your resources right, then you are providing protection too. Okay, let's look at this hardware abstraction in a more detail. As I said, in an operating system, I have many hardware, many processors, my memory, disk, printers, and etc. And managing all these components requires a layer of software, the operating system. I abstract all of these, and the programs running on top of the operating system don't need to know the details of all these different kinds of hardware. Okay, so let's look at this picture. It's a very good picture. At the bottom I have the hardware again, my processors, CPU, and then my memory and my I/O units and etc. Many stuff. And on top of it, I have the software. Okay, I have the software. I have my operating system, and on top of the operating system, as part of the operating system, I have the user interface program. So we are talking about two modes of running here. Okay, a computer can run either in kernel mode or user mode. Do you know the difference? These are both software, but the software can run either in kernel mode or the user mode. Maybe you should know this from the systems programming class. What's a kernel mode, what's a user mode? In the kernel mode,
we interact to user mode, but kernel mode is the core.
What do you mean by core?
Communication between hardware and other software.
In the user mode, you cannot communicate with the hardware. Is that what you mean? Yeah, well, what you are saying is not wrong. It is correct, but I need more details. In kernel mode, there is a very important thing in kernel mode.
Maybe writing drivers.
What do you mean writing the drivers?
Direct access to hardware.
In the kernel mode, you have to write to do everything, okay? Writing to everywhere, okay? In the kernel mode. I can access anything. I can access my memory everywhere. I can do anything with my I/O devices. I can do anything with my CPU and my cores and all the processors, okay? This is the kernel mode. Unrestricted running mode. So only operating systems are allowed to work in the kernel mode. User programs, they cannot work in kernel mode, because when they work in kernel mode, that means that they try to manage their own resources. They try to manage their own resources. Şu telefonla oynama gözümün önünde ya. Kapat onu. Sakla onu. Bir şeyin altına falan. In kernel mode, the operating system works in the kernel mode, okay? And when you are running in kernel mode, you can do anything you like. In the user mode, you are not allowed to do anything you want. For example, you cannot access. You access only your part of the memory. You cannot talk to the hardware, I/O devices, disks, and network drives by yourself. You need to ask the operating system to do your stuff. Okay? So operating systems sometimes work in the user mode too. Okay? Operating system has two parts. In one part, it works in the kernel mode, which is the kernel. Okay? Part of the operating system is the user interface. For example, graphical user interface are parts of the operating system. They run in the user mode. Okay? So our application, my web browser, email reader, or the music player, they all work in the user mode. They talk to the operating system, and operating system switches to the kernel mode. It does everything for you, and it gets results for you, and you get the final results from your operating system. Okay, so all that complex stuff using the computer in a very safe kernel mode has to be done by the operating system. In the 1980s or 1990s, some operating systems, most of the operating systems, especially the PC operating systems, or the user programs, they always run in the kernel mode. The user programs used to run in the kernel mode, so if you make a slightest mistake with your pointers in your C program, your whole computer crashed. Okay? So when you make a mistake, your computer crashes, not your program, but the whole computer crashes, because you have access to all of the resources in your computer. It made the programs faster because you don't need to talk to anybody, but managing your programs and managing your computer was very difficult, because at least 4 or 5 times a day, your programs, your computer used to crash. You would get the blue screen because you didn't have any protection. You didn't have the kernel mode. Okay. So we talked about it. Again, we talked about abstraction. We talked about managing the resources. As a resource manager, operating in an abstraction layer. Okay, this is again a picture from the book. Operating systems turns ugly hardware into beautiful abstractions. These are the ugly stuff. These are beautiful abstractions. Okay, when the application program runs, it sees the world like these, not like that. The real world is like this. Okay, so I feel like this picture. That is, maybe it is helpful to remember. So everybody sign this. Okay, we have only 1, 2, 3, 4, 5 graduate students, and half of the class is missing. So I have 1, 2, 3, 4 people not in this list, but they signed it anyway, so make sure you are registered to this class. Okay, go back to the slides. Again, as a resource manager and an abstraction layer, we have seen operating systems. And as a manager, we say that operating system allows multiple programs to run at the same time. Why do you think we are running multiple programs at the same time? What is our motivation? What is our motivation? Why do we run multiple programs at the same time? When the first computers invented in 1950s, only one program used to run on a single computer. Just one program. And that wasn't enough. Why? Why do we run many programs at the same time on the computer?
Hardware not strong. Passengers.
Hardware?
Not very strong.
Hardware not very strong? Then in that case run a single program. If the hardware is not powerful enough, then run a single program, then it should be enough for your program.
Earlier.
No, I'm talking about today. Why are we running more than one program at the same time?
Because we have very too many resources. And
So-
we can do a lot of
You are
things
saying that
in
because we can. No, that's not a good answer.
Saving time.
What?
Saving time.
Time, saving time. Time of what?
Yani birden fazla işlemi aynı anda yapmaya çalışıyor.
Luxury.
As a luxury, no, it's not a luxury actually. No. What's that again?
Birden fazla işi aynı anda yani kısa sürede.
If we run a single program at the same time, then we have to run it one after the other, right? Or we need many computers to run the same many different things at the same time. So to save time, maybe the maybe answer could be that, because if we run the programs one after the other, then we have to wait for that program to finish. Then I have to run the other one. But sometimes I need to do the two things at the same time. For example, while I am writing my Word document, I like to browse the web so that I can get information from the web and write my report at the same time. If I don't run two programs at the same time, I need two computers, right? I need two computers. Okay. By the way, the reason why they didn't run two programs at the same time in the 1950s is not because the computer hardware was weak. It is because they didn't have the operating systems. They didn't have the operating systems. So most of the time the computer was idle. I mean, during those days, mainframes used to cost like a few $1 million. Okay, so if you keep those computers idle without doing anything for 30% of the time, you are losing $300,000 actually. I mean, because you are keeping your resource idle. When you buy an airplane, you always want your airplane to fly all the time, to carry passengers. If you sit your airplane for most of the time on the ground without doing anything, you are losing money. Computers were like that, but still, they couldn't run more than one program at the same time because they didn't have anything to manage the resources. They didn't have the operating systems. Okay, so we need to allow multiple programs to run at the same time. That means use your resources in an intelligent way, save money, save time, multiple programs. But when you run multiple programs, they need to use the same resource, okay? So it needs to be managed, okay? Manage and protect memory, IO devices, and other resources. Otherwise, if all wanted to use the same part of the memory, if all wanted to use the same disk, IO devices, there will be very ugly problems. We need to prevent those, okay? Okay, so we do multiplexing. Multiplexing means, actually you know this from your computer classes. Okay? Multiplexing means sharing. Sharing resources in two different ways. Sometimes we share resources in time. What do I mean by in time? Sharing a resource in time. Can you guess? What do I mean by sharing a resource in time? Sharing a resource in time. The other one is sharing a resource in space. Maybe I can start from the second one, in space. What do I mean sharing a resource in space? Yes?
Sharing the resource using the same allocation.
Same?
Resources from the same allocation.
Are you talking about the time or space?
The space.
So say it again.
Sharing the same resource from sharing the resource from the same allocation.
Same allocation?
Yeah, we can have many resources to allocate at the same place. And we can
Give me an
access-
example. What do you mean? I mean, give me an example about giving a concrete resource.
Okay, let's say we have resources A, B, C.
No, give me a resource name and continue from that example. For example, disk, hard disk. Yes.
Okay, resource example hard disk.
Yeah.
So we save information, right, in the hard disk.
Yes.
And then we need to access this information at the same time.
Yes.
And this information can be accessed from two parts.
From two
From two sides.
From two parts. What is a part? Process, you mean?
Yes.
Okay.
So we having information.
So where is the space in that one?
The space, the allocation, the resources are allocated. The resources are allocated in the disk hard disk.
If I am using the hard disk and if I am trying to multiplexing or sharing the hard disk in space, that means that some part of the hard disk belongs to a process or a user, and the other parts are they belong to the other processes or the other users. So I am sharing the disk in terms of space. Okay, I'm saying that okay, this space belongs to user A, this space belongs to user B, and the decision who makes that decision is the operating system. Okay, so it makes the sharing of the hard disks possible by, as our friend says, by allocating space for each user. And similar thing can be said for the memory too. Okay, this part of the memory is for you, and this part of the memory is for you. And if you try to access the other people's memories or the hard disk spaces, then you will not be allowed to. Your program will be stopped, and you will not be allowed to do such a thing. The other multiplexing method is the multiplexing in time. For example, for the CPU, I have only one CPU, okay? So I cannot say that, okay, this CPU is for you and this CPU is for you. I cannot say that. Sometimes I could, but if I have a single CPU, I would say that, okay, I have a single CPU, I cannot do the space multiplexing. So what I'm going to do is time multiplexing. I say that, okay, 1/3 of a second, this process will use the CPU. The second third of the second, this process B will use the CPU. And for the rest of the second, another process will use the CPU. So I am multiplexing in terms of time. So the computer operating system does this multiplexing task for us, and it is done transparently for the persons or the processes, so that all the sharing is done in a fair way. Okay, what do I mean by fair? One of them doesn't use all the resources all the time. There is a fair sharing between the users and the process. Otherwise, one of the process uses all the resources, the others are waiting forever. Isn't a good thing? That is not how we run multiple programs or how we handle multiple users. So it is up to the operating system to solve this fairness issue, protection issue. Okay, these are very difficult problems to deal with. Fortunately, people have developed lots of good methods to provide these. Okay. So when I say operating system, some people define it more broadly. In a wide view, okay, when I say Windows, Linux, or Macintosh, OS X, when I say 80 million lines of code, 80 million lines of code for the Windows 8, it includes all the system programs, system libraries, servers, shells, GUIs, etc. Okay, in a wide angle view, they define the operating system as the whole set of libraries, servers, shells, and etc. In the narrow definition, okay, we often mean that only the kernel part of the operating system. This part, only the kernel part of the operating. Remember, user interface is part of the operating system, but it does not run in the kernel mode. In the narrow definition of the operating system, we say that OS often equated with the kernel. In the Linux kernel, the Windows executive is the real operating system. In this book, usually when we say operating system, we take the narrow definition. That is the kernel. We mostly will talk about the kernel when I say operating system. We will not talk about shells or the graphical user interfaces or the servers and that kind of stuff. So we will be mostly talking about in the kernel mode. Okay, kernel mode. Okay, so but for most people, when you say operating system, they literally take the whole operating system that includes the GUIs and the shells and the servers. Okay, so let's go back to operating system history, and let's look at some of the operating systems. 1945 to 1955. Okay, these are World War II years. After World War II, we have the vacuum tube. You know what a vacuum tube is, right? You know what vacuum tube? You know what vacuum tube is? It was It was what they have been using before the transistors. What's a transistor? Transistor is a gate that allows how you that controls how the electricity flows, right? Usually there is a current here, and this is my transistor. Okay. I can control the flow of the current by changing the voltage of this line. This is a transistor. This is the basic building of the modern computers. Before that, there used to be much bigger, more complex components, electric components called vacuum tubes. They were like the light bulb. They were heating up. They were using lots of energy, and they were failing all the time. So in between 45 and 55, you had your vacuum tubes, and there were no programming languages, and we didn't have an operating systems because the computers are so primitive, and whatever you do, you are doing by adjusting your switches and that kind of stuff. Okay, so there is no programming of the computer actually. All the programming was done using the switches and the reconnecting the cables. Okay, so some electromechanical computers were from those years. Electromechanical computers, you do your computation using your mechanic stuff. Actually, I have a small. Where is? Okay, 1956 electromechanical.
So the restoration of the Frieden STW
1956 Frieden STW
demo some of the
calculator.
functionality of the machine. So from the serial
So
number,
it is not.
I know this
You don't
was built in 1956.
You don't program this kind of computers. Everything is already there. You just push buttons and it just works. There is no operating system. It has single task. Okay, so you cannot run more than one program on this kind of a computer because whatever it can do, it is already fixed. You don't program it. You just do addition, multiplication, that kind of stuff.
And happened to come with the original manual.
So the guy has the manual
how
too.
to use the machine. So I'm going to do some of the pages in there, so it explains what all the buttons do. And it starts, of course, with a simple addition: 3279 plus 1432 minus 804.
So he's gonna do a simple addition.
So it's pretty straightforward. So here is how you put the decimal points. Those are actually just reminders, visual reminders.
So you adjust your decimal points. He needs just 2 decimal points.
So set them with 2 decimal
So this line is for the decimal
and
points.
off we go. 3270. Let me clear the keyboard with that button down, so it clears the keyboard after each operation. 3279. So there's one number per column, right?
So that's the number of columns. Yes.
Clears a column, and that locks a column.
Yeah.
Okay, 3279. Big plus button. There you go. It put it right at the top. Plus 14. 32 plus,
so it added those 2 numbers, 4711. So this is how it does the addition. Let me show you how it does the
decimal point correctly, and here
multiplication. Oh, okay.
Alright, that's a good one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 8.
What happened?
Put a lot of large
Hocam pausa
numbers, so it takes a while.
Okay.
Large numbers.
So it is going to do
takes a
some
while.
multiplication. The algorithm for the multiplication is
Right.
add that number that many
That's a good
times.
one.
So
And
it
you
is
see how it
mechanically
does
do
it? It
the
does, successive
I cannot show it there.
So it just keeps adding the right number of time in the right
Let me show that to you again.
window. Okay, I have to add 2 decimal points here, 2 decimal points here, that makes 4. And I don't need to clear it because the multiplication button will do it for me. So off we go, 235.
Let me do this, maybe it will work that way.
Oh, it's 127, 6,
Okay.
5, 2, 0. Let's do a big one because those are really fun. Let's
So
do
it is going to multiply
1,
a
2,
big
3,
number
4, 5,
like
6,
this
7,
one.
8, 9, 8. And here, put
It
a lot
is
of
one.
large
It is one
numbers, so it takes a while.
multiplication number here, and the other one comes from there.
Right. That's a good one.
So it's gonna multiply
And you
these
see
two
how
numbers.
it does it? It does successive.
So it keeps adding and adding and adding until this number comes to 0. So it multiplies by adding all those numbers.
So it just keeps adding
So,
the right number of
in
time
1950s,
in, the right.
This was the computer, okay? So if you have a computer like that, there is no programming yet, okay? There is no operating system because all the resources are there, all the hardware is there. There is a very little bit abstraction. Everything is built into the computer. But those were electromechanical and sometimes vacuum tube computers. They were very weak computers. They didn't have much power. In 1950s, then they started having transistors. When they have the transistors, they have much powerful computers. And when they have much powerful computers, that means that they can run many things on a computer. And they started doing this batch system. Batch means that you are running a single program at the same time. No programs are allowed to run at the same time, okay? You run a single program at the same time in the batch system, but you have many programs waiting one after the other, okay? You take one program, you run it, you finish it, and you start the next one, and next one, and the next one. Then we started having these mainframe computers with the transistors, and we have primitive operating systems. These operating systems, I mean, they didn't have any resource management because only a single program is running on the computer. They didn't have to provide any abstraction because all the programs can reach anything they want. But they provided some kind of libraries. People have been using those libraries. And the first high-level program Fortran, and we have these batch systems. And in 1965, things started getting more and more interesting. We have integrated circuits. We have multi-programming now. And we have time sharing. What is the difference between multi-programming and time sharing? Do you know? Multi-programming means that you have more than one program in the memory, okay? And they are multiplexing the CPU. They are not using the CPU at the same time, but one of them is running, then the next one is running, then the other one is running. It's called multiple. What is time sharing then? Yes.
CPU'nun yanılmıyorsam birçok prosese belli bir zaman ayırması. 1000 saniye çalışabilir ama 10 saniye çalışacağım diyor. Sen de 10 saniye, sen de 10 saniye, sonra tekrar geri dönüyor.
Yes.
Tamam.
That's the main difference between multi-programming and time sharing. In multi-programming, one program starts running and it keeps running until it is blocked or it is done. When the program blocked, what do I mean by blocked? Maybe it needs some input-output. When it comes to input-output time, that process is blocked and the other programs start running. In the time sharing, it's not like that. In time sharing, you have maybe tens of users using the same computer at the same time. You cannot allow a single user to use the computer all the time. So everybody has a time on the CPU, and this time is very, very little time, maybe 1/10, maybe 1/100 of a second. So it is done in that way, time sharing. Spooling means that it's very similar to batch systems. Spooling means that processes wait one after the other. For example, printer spooling. You have a single printer, okay? You have a queue in the printer. You send your print jobs to the printer, and they are spooled. They wait their turn. When their turn comes, they start using the printer. This operating system, Multics, is a very important one, okay? It's a very important operating system. In 1960s, at the end of 1960s, this operating system identified all the major operating system problems and provided some kind of a solution. Most of the solutions that we are using today, it comes from this operating system. It is the father of Unix, okay? And you know, as you know, Unix is father of OS 10 and Linux and Windows NT, okay? So they have their roots in this operating system. Commercially, it was not that successful, but technically, in a technical sense, in a technological sense, it was a very, very successful operating system. And Unix name comes from this Multics name. It's a simplified version of Multics, actually. And it was developed at the beginning of 1970s. And then from 80s to present, we have the personal computers, large-scale integration, integrated circuits, large-scale integration. We have operating systems, PC operating systems, DOS, Windows, OS 10, FreeBSD, and Linux. These are the modern operating systems. And they are still using the ideas from this operating system. I mean, there is no, in this book, there is no concept that we can talk about that was not addressed by this operating system Multics. And it was developed in the 1960s, okay? 1960s. Most of the operating systems, actually, concepts, it was developed as part of the Project Apollo when they sent man to the moon, okay? They needed the computers, very sophisticated computers. So most of the technology also developed during those days, 1960s. So the computers, operating systems, most of the programming languages are side products of Project Apollo. Okay. Nowadays, from 1990 to present, we have the mobile computers. The difference between these mobile computers and the other computers is that they are small. They always need to keep track of the battery life. You cannot run a very CPU demanding program all the time on your mobile computer because it eats up all the battery. So the main concern for this kind of computer operating system is the power management. Okay. Before that, we didn't have any problem with the power because you have your electricity connected to your computer. There is no problem with the power. If your computer is producing too much heat, what do? You put them in an air-conditioned room. Okay. You chill them down to 18 degrees, and it solves all the problems. With the mobile computer, you cannot do that. So the operating system needs to be very, very careful in terms of managing the power, okay? Managing the battery life, managing the power. We didn't have that problem before. But the rest of the problems are from those days, 1960s. In fact, I'm going to show you another video. Just go to YouTube and try to watch documentaries on the operating system histories. This is a video from 1964. And I'm going to show you what kind of computers they had those days. And it is not any different from what we have been using.
In Lexington, Massachusetts, a major research organization which has played an important
This is
role
MIT.
in developing this nation's defense system since...
Let me try to go a little bit. This is a mechanical engineering department. They have been using computers, so they had to develop their own systems. This guy, this one, has developed this system that has a graphical user interface, and it has many ideas that we have been using today. So see these all these buttons. Each button has a single function, so operating system is not very sophisticated.
Push buttons, toggle switches. We have several other related devices. This made TX2 a prime candidate for the sketchpad developments back in 1961. And it remained a program in this machine. So oscilloscope here, which is much like a TV setting.
Let me go to, okay, this part is
position where I am now.
Okay.
To any subsequent position of my right pen. This is much like a
It's like a mouse.
Two pins. One is nailed on the
It is doing it on a CRT.
My right pen.
It can move that line. One part of the beginning of the line is fixed.
I lost tracking there. I moved the pen too fast, and that told the computer to stop drawing the line. Well, if you notice, that bright dot will jump onto the line as I get close to it. Well, the dot in the center of the cross, when you get close to the line, jumps over.
So it is catching. It's locking up when it is very close.
At the end point, it is even a higher gravity field to allow us to position the point exactly on the line, or in this case, exactly at the end point.
The guy is saying that we can use this kind of stuff for drawing a CAD computer-aided design materials.
So now I'm going to draw a second line. There we go. And even the third one. Now, in an ordinary pencil and paper drawing, all we have
this is a CRT, very old technology, and it's called light pen. Very cool thing. We don't use this anymore because we don't have CRTs.
And tell the computer to move that point by another push button command. It will move.
You can do this kind of stuff. So
three lines that are attached to it.
we think that these kind of stuff are new, but they are not new. Okay. And all the operating system concepts and these kind of GUI concepts, they were all proposed before. And for the last 20 years, actually, we don't have anything new. What we are doing is that we re-implement whatever was available in the 1960s with the current hardware, like the mobile phones or the small computers or the wearable computers. Okay? That's why it is important to know. That's why it's important to know what was available before, and we keep. What was this here? Okay, he's doing some 2D stuff. Later, I didn't bring the other part here. Later, he's doing some 3D stuff, three-dimensional stuff, and it is not much different than what we are seeing on computers today with the CAD drawings. Again, I'm going to say the same thing. It is important to know the operating system history. Nothing changed much. The problems are the same. Solutions are a little bit different. With the advent of the new hardware technology, maybe, for example, we say that, okay, these touch surfaces, okay, we didn't have those touch surfaces before. We are saying that, but as you see in this example, they didn't have the touch surfaces, but they had those light pens. And I can find other videos where they are using those touch surfaces too. I remember the technology, it was available. Sometimes technologically it catches up, sometimes it doesn't, but most of the ideas are already there. And when the technology is available, you bring up those algorithms, your ideas, and you put them into good use. And if your product is successful, then you become a successful computer engineer or computer industrialist. I mean, Apple didn't introduce anything new to the computer science field or the computer engineering field. They didn't have a single invention. Whatever they did, it was all taken from the history of the computer science, operating systems or the user interfaces. They are just a successful computer company, that's it. But they didn't invent anything. I am not saying that what they did is easy. It is difficult, of course, because they are a multi-billion dollar computer company. But what they did was, okay, they knew what technology was available, what was done before, and how can I apply that idea to the current technology. That was it. So when we are studying this course, we will always talk about the history of the operating system of the computers, and we will talk about how the problems are solved and how the solutions are relevant to current hardware. Okay, that's it for today. As an exercise or homework, go to YouTube, and type operating system history. There are many good documentaries available. Just watch them, and next Monday we will continue from this one. Okay, see you next week.
Aslında soruları çekiyoruz.